Hello my friends and welcome to another episode of SciNick, and this time we're going to be looking at chemistry key processes, specifically at electrolysis, which is part of chemistry paper 1 of AQA if you are doing that. And we're going to look at electrolysis of molten compounds. We're going to look at industrial electrolysis, specifically for aluminium. We're going to look at how we can electrolyze dissolved compounds, and then finally at a skill, which is writing half equations for electrolysis. So electrolysis is where we are using electricity. We're passing it through ionic compounds that are either molten or dissolved in water. We can do either of those. We're going to look at both of those processes in a moment. But when they conduct electricity, what they do is they cause the ions to move to different electrodes where they're discharge producing elements. And so you can see here, really basic diagram. We've got a positive electrode here, and we've got a negative electrode. The positive electrode is called the anode, and the negative electrode is called the cathode. Poor old cath, is always so negative. And what we'll find is that the opposite charged ions will move to the oppositely charged electrode. So positive ions will move to the negative electrode. So we have the positive ions moving to the cathode, and we have the negative ions moving to the anode. That's the simplicity of electrolysis. That's what's happening. But when they get there, they're going to either receive or donate electrons. So gain or lose electrons, so oxidize or reduce, to become elements. And with electrolysis, we need to be able to write half equations to show the transfer of electrons at each of the electrodes. So for each ion. So we just want to write about how the electron transfer is working for an anode or just for the cathode, and we'll get on to practicing that a bit later. So for electrolysis to happen, we have to have a current. And current here is the flow of charge. It doesn't have to be electrons. It could be electrons. It could be ions. It doesn't matter. In the definition of physics, it should be charge. It shouldn't just be electrons. And so if we have a solid ionic compound, let's say solid zinc chloride, it won't electrolyze. It won't have electricity pass through it because that solid ionic compound has a giant lattice structure, as you saw from topic 2. And in that, those ions are not free to move. They're bonded electrostatically, so positive to negative, and they cannot move freely, so they cannot conduct electricity. So this setup here of electrodes in solid ionic compounds in the salt won't conduct electricity. However, if we make them molten, if we turn them into a liquid, then those ions are then free to move, and those ions can therefore conduct electricity because they can move to either electrode. So what we need to have is we need to have inert unreactive electrodes, so a positive and a negative. We need to have our molten compound here, molten zinc chloride, for example, or lead bromide. You might have done or seen zinc chloride being done. And zinc will be Zn, is a metal, so it has a positive charge, and chlorine has a negative charge, and therefore they will move to the respective electrodes. So you'll have at the negative, you'll have zinc building up, and at the positive, you have chlorine building up. So you get chlorine gas and you get zinc metal. It's really simple. So for these molten compounds, working out the products, it's just a case of what they're going to split into. Figuring out that if you've got sodium chloride, you're going to get sodium, which is a metal, therefore it's positive. Chlorine's a non-metal, therefore it's negative. You're going to get this at the cathode. You're going to get this at the anode, and you're going to get sodium as a product and chlorine gas as a product. If you have iron iodide, then you're going to get the same. You're going to get iron formed and iodine formed. It's a lovely way of separating ionic compounds out, but it does use a lot of energy. Now, we've said that it's a nice way of separating out ionic compounds, and it is a process that we use industrially. So this is one example that we need to know, specifically in the AQA course. And aluminium can only be extracted using electrolysis from its ore. Its ore is aluminium oxide, Al2O3, and the reason we can't extract it in another way, which is what we normally do for metals, is using carbon, is that carbon here is more reactive than zinc, iron, lead, tin, copper, so we can use it to extract those because it basically displaces the oxygen that those metals are bonded to. But we cannot use it to displace the oxygen from aluminium because aluminium is more reactive than carbon. So with the Al2O3, we need something more reactive to take the oxygen away. However, carbon isn't reactive enough, so therefore it can't take the oxygen away. So we can't use a displacement reaction, which is what we would normally do with carbon, to extract it. So we have to use electrolysis. But as we said, electrolysis uses lots of energy, firstly to melt the aluminium, because it has a high boiling point, a melting point even, and it also needs a lot of electrical current to run the electrolysis process. So what we do is, to make this work in a really clever way, we actually make the container, the full container here, a negative electrode. So you can see I've got negative signs around it. This is a negative electrode, the whole of the base of the container is. Then we have positive electrodes dipped inside this mixture. And so in this we have our mixture of, actually what we're going to get onto, the aluminium oxide. And we also add something to it called cryolite, which is kind of a less pure sample of aluminium oxide, but it has a lower boiling point, lower melting point even. I've used the wrong term there completely, which is why I'm getting confused. Total melting point. So we can therefore melt it into a liquid aluminium oxide at a lower melting point than the usual form of aluminium oxide we'd use. So we mix aluminium oxide with cryolite, it lowers the melting point, not the boiling point, and that therefore is using less energy and it's cheaper, which is fantastic. And what we get at the end of it is we get this layer of aluminium, melted aluminium, molten aluminium, because it's so hot, which we can then just tap out of this container, and we've got pure aluminium being formed, which is excellent. The equation for this process is here at the bottom. We have Al2O3 going to make aluminium and oxygen. If we're going to balance this, which we have to, we can balance it by making 2 of those, 3 of this, and 4 aluminium. And the problem though with this process, and another problem apart from the cost and using lots of energy, is that the oxygen is forming at the positive electrode. So we get oxygen forming here around these electrodes. These electrodes are made of carbon, and we've got a high temperature. And when you've got carbon and oxygen at high temperature, they're going to burn together to make carbon dioxide. So what you'll eventually see is that these electrodes will start changing shape, and start kind of wearing down and corroding. It is effectively corroding, that the material is getting used up, so they need to get replaced regularly, and that's the final point that the examiners will be looking for. The other type of electrolysis, where you're not just using a molten compound, is when we have it dissolved in water. And when we dissolve things in water, we're mixing them with H2O, and hydrogen splits to H plus and OH minus, which means that the hydrogen ions can bind to the negative part of the ionic compound, and the OH ions can bind to the positive part of the compound, kind of loosely, which is what allows them to dissolve. So the water breaks down, producing H plus ions and hydroxide ions. But the way that this works is slightly different, because in the mix you can have hydrogen ions, hydroxide ions, and for example number 1 here, zinc ions and chlorine ions, which means that when we're electrolyzing this, we've got two positive ions and 2 negative ions, which need to compete for gaining or losing electrons at the electrodes. And so we've got a set of rules, and we'll keep this nice and simple. At the negative electrode, hydrogen is produced if the metal is more reactive than hydrogen. So here's hydrogen reactivity series. If the metal is more reactive than hydrogen, so lead, tin, iron, zinc, basically anything apart from copper, silver and gold, hydrogen's going to get produced. If you had copper sulfate, you'd get copper being produced at that negative electrode. At the positive electrode though, we get oxygen unless the solution contains halide ions, which is anything from group 7. In which case a halogen is produced. So for the first example here of zinc chloride, we have zinc, which is more reactive than hydrogen, so therefore we get hydrogen produced, H2, and we also have chlorine, which is a halide, so we're going to get H2 and chlorine, and we're going to therefore get left with, if we've used up the H2 and the chlorine, we're going to get zinc oxide being zinc hydroxide forming. So what you can do here is, for the other 3 examples, have a little go, see if you can figure out what the product's going to be. I'll pause it here for a second and you can then give it a go. So the products you're going to get here, for the zinc chloride, zinc is more reactive than hydrogen, so therefore you're going to get hydrogen. For the chlorine is there, so you're going to get the halide chlorine gas being formed, so you're going to get those two, and you're going to get zinc oxide forming as well. For the copper chloride, copper is less reactive than hydrogen, therefore you're going to get copper being formed. The electrode would go orange kind of brown for the copper colour. At the positive electrode you've got chlorine, so you're going to get chlorine gas, and we're going to be left therefore with H2O. For copper sulfate, again you've got copper, so if copper's there basically it's going to get formed, so you've got copper, and sulfate, we don't have a halide, so therefore we're going to get oxygen being formed, so copper and oxygen, and then we've got sulfur left over with the water, so sulfuric acid, H2SO4. And for the final one, the lead sulfate, you're going to have lead, which is more reactive than hydrogen, therefore hydrogen getting produced, H2, and we've got sulfate, so again we're going to get oxygen because it's not a halide, and we're going to be left with our lead, and it's going to be lead hydroxide. Hang on, lead sulfate, PbSO4, because we're just figuring out what we've got left. We've used up the hydrogen and the oxygen from the water and the H plus ions and the hydroxide ions, and then we're left with the sulfate and the lead. Wonderful. If you got that right, well done. Okay, the extra skill that we have with electrolysis, which is quite a high level skill, it's higher tier, is writing half equations. And this often stumps people, but it shouldn't have to be. It's not super complicated, and we're going to work through it nice and slowly to make sure we get it right. So in electrolysis, the cathode is donating electrons, because it's negative, therefore it carries many more electrons relatively compared to the positive electrode, which is the anode. And the anode therefore receives electrons. It's positive, it wants to take negatives, therefore it has electrons given to it. And so the half equations basically represent the transfer of electrons at just one electrode, so either at the anode or at the cathode. And basically, if the ion is positive, it must have electrons added to it to make it stable, to make it neutrally charged, sorry, not stable, but neutrally charged, so no positive or a net zero, no gross more negative than positive, for example. If the ion is negative, it must give away electrons, so it has more electrons, it needs to give away them to become neutrally charged, zero charge net overall. So as an example here, this is the overall equation for aluminium oxide. It's not balanced, that's not a worry for the moment, we want to balance the ones in the half equation now. But if we focus just on the aluminium or just on the oxygen, what they're going to do at the electrodes, we can write half equations for these. Here we have at the anode aluminium, so aluminium is going to get attracted to the, I've made a mistake again. It's going to go to the cathode because aluminium is positive. It's going to go to the negative cathode. There we go. So it's going to go to the cathode. It's going to get attracted to that, and it's going to therefore get added to it electrons. It is +3, a 3 plus charge. Therefore, it needs 3 electrons in total to become aluminium, which is neutral charge, zero charge overall. At the other electrode, which is not the cathode, Nick, it is the anode. The oxygen is going to get attracted, which is negative. It is going to have to give away electrons. So you can write it as the oxygen is going then, therefore, to give away electrons. Electrons going to be left over. But oxygen in its element form is diatomic, so it's O2. Therefore, we need to balance it, hence why there's a big 2 in front of the O beforehand, the ions. And therefore, with 2 oxygen ions, it has a total charge of 4 minus, so it needs to give away 4 electrons. And that's nice and balanced. A second example though, if we are going to be doing electrolysis that produces hydrogen and oxygen, here we have 4 hydroxide ions which are going to give away their electrons. This is actually shown in our specification, this example. The hydroxide ions will actually be the things that produce oxygen, so in any example when you're producing oxygen, it's these hydroxide ions that are doing so, and we'll also be getting water. So in any example of the anode where oxygen is being formed, we're also forming water. So 4 OH minus are giving away a total of 4 electrons. We're also getting 1 oxygen and balanced out 2 water molecules. At the cathode, which is negative, we've got 2 hydrogen ions that are going to go to form hydrogen gas. 2 hydrogen ions form H2, which is diatomic. Therefore, each one has a one plus charge. It needs to give away an electron each. So 2 hydrogen ions need to give away 2 electrons. So I'm going to give you some examples to do. Again, give them a try. Pause the video, give them a try, and then I'll give you the answers just to check to make sure you're on the right track. Okay, so if you had a go at these, let's work through how to get to the answers. So zinc oxide here, we need to think about what ions we have. So we have Zn, which is 2 plus typically, and oxygen, which is 2 minus. So at the cathode, which is negative, we're going to have the positive ion going there, which is Zn 2 plus. It's going to go on to form Zn, and to get it from 2 plus to just neutral, we need to add 2 electrons. That's it, job done. For the anode, we have an O2 minus ion, which later goes to form O2. It's diatomic, so it exists as O2. So to balance that on this left-hand side, we need to make it 2 O2. And we need to take away 2 electrons, which from each ion. We have 2 ions, so it would be a total of 4 electrons that would be separated away from the oxygen at the end. For number 2, we've got magnesium, which is Mg. It's in group 2, it's 2 plus, and chlorine is minus. So at cathode would have the positive magnesium, Mg2 plus. I'm going to make Mg, and to add to that we need to add 2 electrons to counter the 2 minus, the 2 plus even. So we end up with this. And at the anode we have Cl minus reacting to form Cl2, so we need 2 ions of chlorine, which are both negative. If we take away the negative charge from each of those, we need to take away 2 electrons, which gives us those at the end. And the final one here is probably a bit of a challenge, but in sodium chloride, which is aqueous, so it means it's dissolved in water, we also have the hydroxide and the hydrogen ions to consider. And we need to be able to work out what product we're going to be getting. So in this case with sodium, sodium is more reactive than hydrogen, so we're going to get hydrogen gas, because that's going to be our positive product. And chlorine is a halogen, so we're going to get chlorine gas too. So we've got hydrogen and chlorine, and those are the two that we're going to write these half equations for. So at the cathode, we'll have the positive, which is H+, goes to make H2, and so to get rid of our positive charge, we need to balance them first. So we've got 2 hydrogen atoms on the right, so we need 2 hydrogen ions on the left, and we need to add an electron for each one, and that's the first part done. For the anode, we have chlorine, so it's the same as above for number 2. Chlorine, which is minus, goes to make Cl2, which is a diatomic atom, diatomic molecule even, and we need therefore 2 ions, and it's going to need to release 2 electrons to become balanced, stable, neutral. The extra thing you might be asked about here are 2 terms, oxidation and reduction, and we can just add this on here. So in the good old way of remembering it, oil rig, oxidation is the loss of electrons and reduction is the gain of electrons. So oil rig, oxidation is loss of electrons, reduction is the gain of electrons, and then you can start thinking, well, which ones here are being reduced, which ones are being oxidized. So for example here, zinc is having electrons added to it, so it's gaining electrons, therefore it's being reduced, it's reduction. Oxygen is having electrons taken away from it, so it's being oxidized. Simple as that. Thank you for watching, guys. If you've got any challenges, any questions or queries, please do put them in the comments below. Otherwise, do like and subscribe and check out the other videos I have.